let's see if we can learn a thing or two about partial fraction expansion, or sometimes it's called partial fraction decomposition. Partial fraction expansion. The whole idea is to take rational functions, and a rational function is just a function or expression where it's one expression divided by another, and to essentially expand them or decompose them into simpler parts. And the first thing you got to do before you can even start the actual partial fraction expansion process is to make sure that the numerator has a lower degree than the denominator. And the situation, the problem that I've drawn right here, or I've written right here, that's not the case. The numerator has the same degree as the denominator. So the first step we want to do to simplify this and to get it to the point where the numerator has a lower degree than the denominator is to do a little bit of algebraic division. And I've done a video on this, but it never hurts to get a review here. So to do that, we divide the denominator into the numerator to figure out the remainder. So we divide x squared minus 3x minus 40 into x squared minus 2x minus 37. So how many times do you look at the highest degree term? So x squared goes into x squared one time. 1 times this whole thing is x squared minus 3x minus 40. And now you want to subtract this from that to get the remainder. And see if I'm subtracting. So I'm going to subtract, and then minus minus, that's a plus, and then you can add them. These cancel out. Minus 2x plus 3x, that's x. Minus 37 plus 40, that's plus 3. So this expression up here can be rewritten as, let me scroll down a little bit, as 1 plus x plus 3 over x squared minus 3x minus 40. And it's important to keep, this might seem like some type of magic thing I just did, but this is no different than what you did in the 4th or 5th grade, where you learned how to convert improper regular fractions into mixed numbers. If I had, let me just do a little side example here. If I had 13 over 2, and I want to turn it into a mixed number, what you do, you probably do this in your head now, but what you did is you divide the denominator into the numerator, just like we did over here. 2 goes into 13. You say 2 goes into 13 6 times. 6 times 2 is 12. You subtract that from that, you get a remainder of 1. 2 doesn't go into 1, so that's just the remainder. So if you wanted to rewrite this, it would be the number of times the denominator goes into the numerator, that's 6, plus the remainder over the denominator, plus 1 over 2. And when you did it in elementary school, you would just write 6.5, but 6.5 is the same thing as 6 plus 1/2. And that's exactly the same thing we did here. The denominator went into the numerator 1 time, and then there was a remainder of x plus 3 left over, so it's 1 plus x plus 3 over this expression. Now we see that the numerator in this rational expression, the numerator does have a lower degree than the denominator, right? The highest degree here is 1. The highest degree here is 2. So we're ready to commence our partial fraction decomposition. And all that is taking this expression up here and turning it into 2 simpler expressions where the denominators are the factors of this lower term. So given that, let's factor this lower term. So let's see, what 2 numbers add up to minus 3? And when you multiply them, you get minus 40. Let's see, they have to be different signs, because when you multiply them, you get a negative. So it has to be minus 8 and plus 5. So we can rewrite this up here as, I'll switch colors, 1 plus x plus 3 over x plus 5 times x minus 8. Right? 5 times 8 is minus 40. 5 times negative 8 is minus 40. Plus 5 minus 8 is minus 3. So we're all set. Now I'll just focus on this part right now. We can just remember that that 1 is sitting out there out front. This is the expression we want to decompose or expand. And we're going to expand it into 2 simpler expressions where each of these are the denominator. And I will make the claim, and if the numbers work out, then the claim is true. I'll make the claim that I can expand this or decompose this into 2 fractions, where the first fraction is just some number a over the first factor over x plus 5 plus some number b over the second factor over x minus 8. That's my claim. And if I can solve for a and b in a way that it actually does add up to this, then I'm done. And I will have fully decomposed this fraction, I guess is the way. I don't know if even that's the correct terminology. So let's try to do that. So if I were to add these two terms, what do I get? Well, when you add anything, you find the common denominator. And the common denominator, the easiest common denominator, is to multiply the two denominators. So let me write this here. So a over x plus 5 plus b over x minus 8 is equal to, well, let's get the common denominator. It's equal to x plus 5 times x minus 8. And then the a term, we would, a over x plus 5 is the same thing as a times x minus 8 over this whole thing, right? I mean, if I just wrote this right here, and you just canceled these two terms out, and you would get a over x plus 5. And then you could add that to get the common denominator, x plus 5 times x minus 8. And it would be b times x plus 5. Right? Important to realize that, look, this term is the exact same thing as this term if you just cancel the x minus 8 out. And this term is the exact same thing as this term if you just cancel the x plus 5s out. But now that we have an actual common denominator, we can add them together. So we get, let me just write the left side here over a over x plus 5. Oh, sorry. I want to write this over here. I want to write x plus 3 over x plus 5 times x minus 8 is equal to the sum of these two things on top, a times x minus 8 plus b times x plus 5. All of that over their common denominator, x plus 5 times x minus 8. So the denominators are the same. So we know that this, when you add this together, you have to get this. So if we want to solve for a and b, let's just set that equality. We can ignore the denominators. So we can say that x plus 3 is equal to a times x minus 8 plus b times x plus 5. Now, there's two ways to solve for a and b from this point going forward. One is the way that I was actually taught, in the 7th or 8th grade, which tends to take a little longer. Then there's a fast way to do it, and it never hurts to do the fast way first. If you want to solve for a, let's pick an x that'll make this term disappear. So what x would make this term disappear? Well, if I say x is minus 5, then this becomes 0, and then the b disappears. So if we say x is minus 5, I'm just picking an arbitrary x to be able to solve for this. Then this would become minus 5 plus 3. Let me just write it out. Minus 5 plus 3 is equal to a times minus 5 minus 8. Let me just write it out. Minus 5 minus 8 plus b times minus 5 plus 5. And I picked the minus 5 to make this expression 0. So then you get, pick a brighter color. Minus 5 plus 3 is minus 2 is equal to, what is this? Minus 13a plus, this is 0, right? That's 0. Minus 5 plus 5 is 0. 0 times b is 0. And then you divide both sides by minus 13. You get, well, negatives cancel out. You get 2 over 13 is equal to a. And now we can do the same thing up here and get rid of the a terms by making x is equal to 8. If x is equal to 8, you get x plus 3 is equal to 11 is equal to a times 0, plus b times, what's 5? 8 plus 5 is plus b times 13. The third b looks a bit like a 13. And then you get 11 is equal to 13b. Divide both sides by 13. You get b is equal to 11 over 13. So we were able to solve for our a's and our b's. And so we can go back to our original equation, and we could say, wow, this just has to be equal to 2 over 13. And this just has to be equal to 11 over 13. So our very original thing we wrote up here can be decomposed into 1, that's this one over here, plus this, which is 2 over 13. I'll just write it like this for now. 2 over 13 over x plus 5. You could bring the 13 down here if you want to write it so you don't have a fraction over a fraction. Plus 11 over 13. Plus 11 over 13 times over x minus 8. And once again, you could bring the 13 down so you don't have a fraction over a fraction. But we have just successfully decomposed this pretty, I don't want to say that we necessarily simplified it, because you could say, oh, you only have one expression here, now I have three. But I've reduced the degree of both the numerators and the denominators. And you might say, well, Sal, why would I ever have to do this? And you're right. In algebra, you probably won't. But this is actually a really useful technique later on when you get to calculus and actually differential equations. Because a lot of times it's much easier, and I'll throw out a word here that you don't understand, to take the integral or the antiderivative of something like this than something like this. And later when you do inverse Laplace transforms and differential equations, it's much easier to take an inverse Laplace transform of something like this than something like that. So anyway, hopefully I've given you another toolkit in your, or another tool in your toolkit, and I'll probably do a couple of more videos because we haven't exhausted all of the examples that we could show for partial fraction decomposition.